Dear friends, in earlier two videos we have seen probability and random variable. This is my third video and on probability and random variables. Let us see more on axioms of probability, properties of distribution function and properties of density function. So this is my third video on probabilities and random variables. So axioms of probability, let us see axioms of probability. So the first axiom is the probability of any event, it is always lies between 0 and 1. At the least it is 0 and at the most it is 1. The probability of sample space has to be 1. Probability of sample space has to be 1. Sample space, we know, collection of all possible outcomes. The probability of that sample space is always 1. And the third axiom is probability of A union B. If A and B, they are not mutually exclusive, then which is equal to probability of A plus probability of B minus probability of event A intersection, not union, it is intersection, A intersection B. So whatever is common between A and B, that region, probability of that region. So probability of A plus probability of B minus probability of A intersection B. If suppose we are having n events, A1, A2, A3, An, all they are mutually exclusive events, all they are mutually exclusive events. In that case, probability of A1 union A2 union A3 on and so on union An, the probability of all these together, all these unions, probability of all these unions is equal to probability of individual addition of probability of individual events. So probability of A1 plus probability of A2 plus probability of A3 and so on plus probability of An. If events are mutually exclusive, there is a addition of respective probabilities of individual outcomes, individual events, addition of probabilities of individual events. A1, A2, A3, An, all these are events, and if they are mutually exclusive events, in that case the probability of union of all these events is equal to addition of all probabilities. Now I will be talking about conditional probability of two events. When A is probability of A, when A is B is given, how to find that probability? The conditional probability of A given B is defined as like this. Probability of A when B is known to us is defined as probability of A intersection B divided by probability of B. So when sometimes the probability of B is given and the event A is known, so probability of B given A is equal to probability of A intersection B divided by probability of A. A and B, if they are independent events, then probability of A intersection B is equal to probability of A into probability of B. If suppose A and B, they are mutually exclusive events, in that case probability of A intersection B is 0, or we can say that probability of A union B is equal to probability of A plus probability of B. So we have seen axioms of probability, we have seen conditional probability. After this, now we will go to probability distribution functions, some of the properties of probability distribution functions which are required many times while applying or studying the various concepts related to probability distribution function. Now let us see the important properties of probability distribution function, which is also called as probability cumulative distribution function. So here cumulative distribution function, we have seen definition which is denoted by fx of x, which is equal to probability that capital X is taking value less than equal to small x. So we have seen the definition of probability distribution function. In fact, we have also seen problems on probability distribution function. There are some important properties which are many times required in practice. I am just discussing those properties in this video. So the first property is the probability density distribution function. Probability distribution function, which is also called as cumulative distribution function, is non-decreasing function. So a non-decreasing function means whatever value it has in the previous interval, in the next interval that value is either same or it will increase, but it will never go down, because we have seen probability distribution function, as we proceed we are adding the probabilities of new event into the earlier events. So definitely it is non-decreasing function. So its value, either its value increases or it remains same. So that is what we are saying, non-decreasing function of x. The second property is probability distribution function fx of minus infinity. The meaning thereby here is probability that a random variable is taking value less than equal to minus infinity. So that event does not exist. That event does not exist. So probability of non-existing event is 0. Probability of non-existing event is 0. So fx of minus infinity is 0. So next property, which is again related to probability distribution function, fx of infinity. So fx of infinity is, it means it is the probability of sample space. Fx of infinity, it means the probability that random variable taking values less than equal to infinity. So here all values are possible. So taking any value between minus infinity to plus infinity. So here the probability that fx of x, it has to be 1. It is covering all the events. We can say that entire sample space is coming into picture. So fx of infinity is equal to 1. In the earlier video we have seen the problem on probability density and distribution function, where we have taken example of die. So probability of individual outcome was 1/6, probability of taking phase f1, probability of taking f2, and so on f6. The probability was 1/6 because we took die to be a fair die. So here less than infinity, it means if I take the example of fair die, x is taking value less than equal to infinity, it means it is covering entire all the outcomes of the sample space. So we can say that the probability value of probability distribution function when small x is taking value infinity, so it means that it is addition of all probabilities up to infinity, so it has to be 1. So that is the explanation for fx of infinity. So fx of infinity means probability that a random variable capital X is taking value less than equal to minus less than equal to plus infinity. So it is coming from entire real axis is coming into picture. So we are adding all the probabilities of outcomes which are taken by random variables. So random variables is giving the values to each of the outcomes. In case of die throwing experiment there are 6 outcomes. So probability that random variable is taking value less than infinity, it means that it is covering all the outcomes and their corresponding values in terms of mapping. Because of random variable we are getting the values to each of the outcomes. So if I add all these probabilities, probability of appearance of f1, probability of appearing of f2, and so on. So when I say x is less than infinity, all entire sample space come into picture, and probability of sample space is equal to probability of addition of probability of individual elements of the sample space. So that is why this is 1. So we have seen that. We have also seen in case of density function, when we define density function, we said that density function is defined as it is the derivative, or it is a differentiation of distribution function. So dfx dx is equal to fxx, where this x is a random variable and it is the value taken by the random variable at particular instant. So again here fxx, this is also random variable, and this is the value x. The definition of probability distribution function is probability that random variable x is taking random variable capital X is taking value less than equal to small x. Now here this is distribution function, so it is density function fx of x. Density function can be obtained by differentiating distribution function. Distribution function is also called as commutative distribution function. So we here only thing is that we need to have the differentiation possible. So at all points where fx is differentiable. And one more property again we require many times is if it is a random variable which is discrete in nature and taking values x1, x2, x3, xn, and these values are such that x1 is less than x2, x2 is less than x3, and so on, xn is greater than xn minus 1. So in this case, if you want to find out the probability of particular probability that random variable is taking particular value, so probability that random variable is taking value xi, which can be obtained by taking the difference of distribution function evaluated at xi and minus distribution function evaluated at xi minus 1. So probability at particular instant x equal to xi, if random variables are discrete in nature, then in that case that probability can be obtained by putting capital X equal to xi and computation of density function minus computation of distribution function minus distribution function evaluated for random variable taking value less than equal to xi minus 1, which you can see if you expand this you will be getting in terms of density function. If I try to write this in terms of density function, so here xi, so random variable taking value less than equal to xi minus infinity. So here it is a distribution function, so we have to corresponding is density function dx minus infinity to xi minus 1 fx of x dx. So here it is fx of x. So this is what density function evaluated for over this interval minus density function evaluated over this interval. We can write p of, if it is a random variable is discrete, we can write p x equal to xi. Probability at particular value, random variable is taking particular value xi, can be obtained by using this expression. So okay. Now let us see the major properties of probability density function. We have seen major properties of probability distribution function. Now we'll describe, or I will explain the properties which are satisfied by density function when random variable is continuous and when random variable is discrete. When random variable is continuous, then your density function fx x is always greater than or equal to 0 for all x belonging to R. R is maybe minus infinity to plus infinity or a particular region. So density function is always taking value which are non-negative. Density function is always taking value which are non-negative, greater than equal to 0. And we say that density function is a valid density function if it is integrated over the interval, given interval. If it is integrated, the result has to be 1. Density function is said to be valid density function if it is integrated over the given interval, the result has to be 1, or area under the function fxx has to be 1, then we can say that it is a valid density function. And the first property is it should be greater than equal to 0, so it should be non-negative. And in case of discrete random variable, the density function in case of discrete random variable, density function has to satisfy following properties. Here we are describing in terms of probabilities, all probabilities p0, p1, p2, p3, p4, for all I, whatever probabilities are there, all probabilities either they are to be 0 or greater than 0. So pi must be greater than equal to 0 and addition of all probabilities must be 1. So whenever random variable is discrete, we are talking about their probability, and whenever they are continuous, we are talking about density functions. So we talk about individual probability when it is discrete, and whenever it is continuous, we talk about its density function. So density function is available in terms of probabilities in case of discrete random variable. So these are the some of the major properties of density function. We have also seen that we can write density function and distribution function, relation between density function and distribution function. As I told you that while describing the probability distribution function, the derivative of probability distribution function is nothing but density function. When I define density function in terms of distribution function, fx of x, it is defined as integration minus infinity to x minus infinity to x. So whenever I am defining distribution function fx x, which is nothing but minus infinity to x fx x dx. I'm sorry, it was written as small f. Small f is for density function and capital F is for distribution function. So distribution function in terms of density function can be written like this. Whenever we have a distribution density function, we can find distribution function by using this relation. So fx x, this is x is for random variable, capital X. So fx suffix is denoting the random variable. The x is the value, that probability that random variable x is taking value less than equal to small x, So we are going from minus infinity to small x, whatever may be its value. Integration of probability density function from minus infinity to x, that gives the value of distribution function, which is nothing but probability that x, capital X, is taking value less than equal to small x, which can also be written as probability that it is greater than minus infinity to less than equal to small x. I would like to add one more thing here. Whenever we are talking about probability at a single point, in case of continuous random variable probability, we are considering single point, that time the probability is 0. So in case of random variable which is continuous in nature, so these equations, they are all are having same meaning. If I say x1 is greater than less than equal to x1 is less than equal to capital X is less than x2, or we can write probability that x1 is less than capital X is less than equal to small x2. So all they are same, because probability of individual probability of individual point is 0, or integration of individual point is 0. Whether this point is included or not, the result is not going to change, because integration of a single point is 0. In case of discrete domain, it makes difference, but in case of continuous domain, if random variable is continuous, in that case, if I write this, every equation has the same meaning. But if it is a discrete domain, if I say here greater than x1 and less than x2, so x1 plus something greater than x1 means x1 is not included, less than x2 means x2 is not included, in case of discrete domain. But here in continuous domain, it is a single point and integration of a single point is 0. So that is why whenever if you are talking about x is continuous, equality doesn't makes any difference. Equality, even if equality is written or not written, it is not going to make any difference. Okay, here I am saying no equality, here equality, one equality, here again one equality, and last one is x1 is, again I can say this is also meaning is same. All expressions, they have the same meaning if the random variable is random variable is continuous. If it is discrete, they have the different meaning. This equation is not same as this, or this equation is not same as this. All these are different equations if I take the random variable to be discrete. Okay, this was the small final point which I wanted to share with you. Now let us see when there are two random variables. One is expressed in terms of linear combination of other. So in that case, how their probability distribution function and probability density functions, they are related, that is what I am going to explain. Let us say there are two random variables x and y, where y is equal to ax plus b. So y is a random variable, x is also a random variable. This is random variable, this is also random variable. A and b, they are constants. So random variable y is expressed as linear combination of random variable x. So y equal to ax plus b. So we know that probability distribution function of random variable y, fyy, is probability that random variable capital Y is taking value less than equal to small y. You can write like this. So we know that random variable y in terms of x, so ax plus b is less than equal to small y. Then we can write probability, this can be simplified. We can take b towards that side. Ax is less than equal to y minus b. So fyy can be simplified and can be written like this. Now here there are two possibilities. A is positive, there is no issue. If a is negative, there is an issue. Let us consider that a is greater than 0. Let us assume that a is greater than 0. A is greater than 0, and in that case your equation, this equation will be written as, that equation becomes fyy is equal to fx, that equation becomes probability that y is less than or equal to y minus b by a. If a is positive, equality remains as it is. If a is negative, we have to change the equality. So let us assume a is positive and write the equation for fyy. So by definition, if you see this, it is nothing but so this is actually x, it is nothing but probability of x y minus probability distribution function of random variable x, okay, taking value less than equal to y minus b divided by a. So this is the fyy when a is positive. Probability distribution function of y can be written in terms of probability distribution function of x when y equal to ax plus b. Now another situation when a is not positive, in that let us consider the case where a is negative. So a is less than 0. So what happens to this one, fyy? We were having this equation at our disposal, ax less than equal to y minus b. Here if a is negative, the equality will not be same, so it will change the equality. So we can write probability that x is greater than y minus b by a. So this greater than sign will come into picture instead of less than equal to. So this is probability that random variable x is taking value y minus b by a. So in this case we can write, because we know that the probability that we know that probability that random variable taking value greater than a plus probability that random variable x taking value less than equal to a, this is the general formula which is equal to probability that random variable taking value greater than a means a to infinity and less than a minus infinity to a. This result is always 1. So we'll be using this result here. This a and this a, they are not related, they are different. So in this case what we can do is we can write a is negative, then fyy can also be written as 1 minus fx of y minus b by a. I have dropped one step here, so result will be like this: 1 minus fx of y minus, so x is greater than, let us say this is a, x is greater than a, it can be written as 1 minus probability that x is less than, okay. So this is nothing but, I dropped one step but that step is important, let me write that step: probability that x is, this is greater, so less than equal to y minus b by a, we can write this, so which is nothing but 1 minus probability that so directly write down the definition, so nothing is to be changed. So fx of y minus b by a is equal to fyy. So this is the density distribution function, not density function, this distribution function when a is negative, and already we have obtained distribution function when a is positive. So when we go for finding the density function fyy, so in that case I said that it is the derivative of your density function. So here y is given as ax plus b, so we know that dy by dx is equal to a, which implies dx by dy is equal to 1 by a. So derivative of x with respect to y is this, so dy by dx, random variable is taking, y is taking value y and capital X is taking value small x, so it will be written like this. So derivative is dx by dy is 1 by a. So now we are having expression at our hand, and we have also derivative dx by dy is 1 by a. So let us write first expression for distribution function fx, distribution function fy when a is positive and a is negative. This is fx of y minus b by a when a is positive, and here it is 1 minus the fx of y minus b by a when a is negative, okay. So we can take a is greater than equal to 0 here and a is less than 0 here. So when I am taking the derivative with respect to y, dfy y divided by dy is equal to, if you take here derivative with respect to y, so what we get, fx of y minus b divided by a. So if I take derivative dy, so it is 1 and divided by 1 by a is a constant, so it is 1 by a. So 1 by a, which is the result. And in second case, if it is dfy divided by dy, which is equal to minus 1 by a fx of derivative of y, okay, with respect to derivative of this fx is capital F, x is fy, and into derivative of bracket is again in this case 1 by a y minus b divided by a. This one derivative of 1 is 0 and this minus sign, and derivative of this bracket is 1 by a. So we can write this is nothing but fx of x, fx of, we can say, sorry, fx fy fyy, this is also fyy. So in together we can write both these equation, and that equation is fyy is equal to 1 by mod of a fx of y minus b by a. So distribution and density functions of random variable y we can write in terms of distribution and density function of random variable x. So in here, if one random variable is expressed in terms of other and they are linearly connected, then how to find the density function and distribution function of resultant random variable. Here y equal to ax plus b, so we got the distribution function of random variable y as well as density function of random variable y in terms of random variable x.